Okay, let's start with a couple of questions, conceptual questions. So let's look at this question. So what is the change in momentum of that cart? So the cart hits the wall and it bounces back. So what's the change in momentum? Is it A, B, C, or D, or E? E? Okay, so let's see if it is right or not. So initial momentum is 2 times 10, mass times velocity is 20 kg meters per second, and it's going to the left, so we need to consider negative sign for that. It's very important. And mass doesn't change, still 10 kilogram. So the final momentum is 10 times 1 is 10 kg meters per second. Okay, so that's PF, that's PI. So change in momentum is PF minus PI. That's the change. So change would be then 10 minus. So PI is minus 20. So minus 20. So 10 minus and minus is plus. So it's 30. Yes. So that's, I don't know why it's not responsive. Okay. That's, yeah, this tab and pen doesn't like the PowerPoint. Okay. So I don't know, it's not. Okay, so that's right, 30. Okay, next question. A rubber ball experiences the force shown in the figure as it bounces off the floor. What is the impulse on the ball? So what's the answer? Should be pretty straightforward. If you remember, impulse or change in momentum are same. And if you have a graph, impulse is given by area under the curve, so area of the graph. So you need to find the area. Area is 1/2 base times height. Base is 8. Height is 300. And then half. And then you need to convert this millisecond to second. So that will be 1/2 8 times 10 to negative 3 seconds. Height is 300. So that gives us, is that 1.2? Okay, 1.2. So that's okay. Okay. Come on. What happened? Stock. Next. Okay. So same question. Now we want to find the average force. So we know the maximum force is 300, but we want to know the average. Okay, average is like you're adding all these forces. There are number of forces here. It's changing, and then divide by how many number of forces you are considering. So how do you get the average force? So when the force is changing, you can find the impulse by using this formula. So impulse is force times time, but if the force is not constant, you can say it's average force times time. Okay? So we want to find average force. Average force is impulse over time. We already found impulse in the previous question. Impulse was 1.2 kilogram meters per second, and then time force is impulse over time, and then the time. What's that, sorry? Are we going to need to convert it to seconds again? Yeah, because we want to express force in Newton. So to convert, to express this in Newton, we need time in seconds. So 8 times 10 to negative third. So what will you get? Yeah, 150. Okay. So this is a conceptual question. A heavy truck and a small car roll down a hill at the same speed. So you have a big truck and a small car. They have same speed, V and V. One has big mass, other one has small mass. Compare the force need to stop the car with the force need to stop the truck. Which one would be greater? It's not a tricky question. You should know this even by using your common sense. Truck, yeah, so that's truck. And the physics behind that is to stop the truck, you need impulse. You need to apply impulse. Impulse is force times time. Okay, since so you have mv final minus mv initial. Mv final would be 0 because you want to stop that. Okay, so this force. Time is also same. That means force depends on mass. So for both, velocity is same, time is same. So this force depends on how big the mass is. Bigger the mass, more force you need to stop the car. Okay. So we talked about elastic collision, and in inelastic collision, what can you say about the momentum in elastic collision? Less? Do you guys agree? For both elastic and inelastic collision, momentum is conserved. Okay, momentum remains same whether it's elastic or not. But energy is conserved only in elastic, okay, not in inelastic. Some of the energy is lost in form of heat and sound in case of inelastic collision. Okay. So in this case, we are asked to compare the momentum. So final momentum would be same as initial momentum for both elastic and inelastic collision. Okay. So which concept or principle best illustrates the usefulness of automobile airbags? So the concept behind using airbag is to decrease the impact force, and we talked about this last time. How can you decrease the impact force? You can decrease the impact force by slowing down or increasing time, right? Because stopping means you are changing the momentum. You're going from initial momentum to final momentum. That's the thing you are doing, and for that you need this impulse. And you can decrease this. You need certain impulse. Okay, let's say 1,000 impulse, 1,000 Newton second. So you can get this impulse by increasing the time. Let's say 10 second over and giving 100 Newton. Okay, you can do that. Or you can also do like 1,000 Newton over 1 second. So this has more impact force. This one has less impact force. So longer the time, less is the impact force. Shorter the time, more is the impact force. So basically, that's what you are looking for. Okay, you want to increase the time to decrease the force. So the relevant principle here is impulse momentum theorem. Okay, so those are some of the review questions. Now let's look at worksheet 14, worksheet 15, although it says worksheet 14, but it's supposed to be 15. So if you are on Zoom, you can download this from Blackboard. So there are some applications of conservation of momentum. So let's look at the first question. So a truck going at 11 meters per second runs into 975 kilogram stopped car, and then they stick together. How fast the pair move just after collision? So we want to find the final velocity of the combined truck and car after collision. So the idea is pretty straightforward here. Conservation of momentum tells us momentum before collision is equal to momentum after collision. So momentum before collision is momentum of the truck. Let's say this is A and this is B. That's A, that's B. So momentum of A plus momentum of B. Momentum after collision is momentum of A plus momentum of B. So this is initial, so I. This is final, so F. Momentum of A initial is mass times velocity, mass times velocity, mass times velocity, mass times velocity. So this is mass of A, that's mass of B. Okay, mass of A, mass of B, velocity of A, velocity of B, velocity of A, velocity of B. So this is initial, final. Okay, that's the conservation of momentum. You don't need to memorize the formula. I'm just showing you how you can get this formula from the conservation of momentum. Okay. So initially the car is at rest, so this is 0, velocity of b is 0, and then after they collide there will be a single mass. That means the velocity would be same for both. Okay, you can just write this as Vf because it's common. You don't need to say Va or Vb, just call it Vf, same. So we want to find Vf. You can plug in the numbers here, but if you want to simplify, you can also simplify this. So Ma plus Mb, take this common term Vf outside the parentheses, and then write this in terms of Vf. So to write this in terms of Vf, you can divide both sides by Ma plus Mb. We cancel that and that. So Vf, which is what we want, is Ma Vai over Ma plus Mb. Okay, and then you plug the numbers in. Mass of A is 3470 kilogram. Speed or velocity of A initial 11.0 meters per second. Mass of car A 3470. Mass of car B 975 kilogram, and then you do the math. Okay, so that'll give you 8.59 meters per second. So number 2 is similar to what we did in lab yesterday or on Wednesday. The only difference is on number 2 it's inelastic collision. The one we did was elastic, they bounced back, but here the trains get stuck, they don't bounce back, and then they move as a single object, single mass. So again, we can use the same formula, this one, for, or not this one, the top one. Okay, that's the formula for conservation of momentum. So mass of first train, velocity of first train, which is initial, mass of second train, velocity of second train initial, that is equal to the final momentum would be momentum of the combined mass, which is m1 plus m2. That's the combined, and the final velocity of that combined one. Okay, so again this is before collision, and this is after collision. Okay, so rest is just plugging in the numbers. It's plugging in the numbers, but one thing is very important here. You need to keep that in mind. That is, this train is moving to the right, and this train is moving to the left. Okay, so that means this the velocity of this car or train would be negative. The velocity of this would be positive. If the question says negative, that's fine. You can just plug in the number, negative number. But if the question says positive, then you need to put negative sign for that number, even if the question doesn't give you the sign. Although in this question, the question tells us that it's a negative number. But in some problems, it may not tell you it's negative. You should know it by using the rule that negative left side is negative. So you can plug the numbers at this point, or if you want, because we are finding VF, you can just write this in terms of VF by dividing both sides by M1 plus M2. So you get M1 V1I plus M2 V2I over M1 plus M2. Okay, so you can plug the numbers in. Okay, so I didn't read the question carefully. So VF is given actually. VF is given. We are finding the initial velocity. Yeah, so that's right. So that means I need to rearrange the equation in a little bit different way. Okay, so this won't work. Let me just go back. Okay, so in this case, we want to find initial velocity of the second cart. So this is what we want to find. So we want to write the equation with this one on the left and everything else on the right. So what should I do for that? So subtract this thing on both sides. Okay, so M1 V1I. So subtract this on right and left. M1 V1I plus M2 V2I. M1 plus M2 VF minus M1 V1I. Okay, just subtracting the same term on left and right, and then you can cancel this one and this one, and then because I want to get this one, so you want to divide both sides by M2 to get rid of M2. So then cancel M2 and M2. You get V2I is equal to M1 plus M2 V final minus M1 V1I over M2. Okay. Now you can plug in the numbers. So M1 is 2 times 10 to 4th kilogram. M2 is 4 times 10 to 4 kilogram. V final is negative 0.25 meters per second minus M1 2 times 10 to 4th kilogram, and V1I, initial velocity of the first one, 1.5 meters per second, that over M2, which is 4 times 10 to 4 kilogram. So that will give you V2I, which is, so I got this answer, negative 1.125. I would like you to confirm that. Okay, I may be wrong. That's what I got when I did the calculation. And the negative sign implies that the second card is moving to the left. Okay. Initially. Okay, that's good. Okay, let's look at third one. I think I mixed up the names here. So initially I had Julie and Mike, but then it changed to Sandra and David. So you want to make the names same. So you can replace Mike by David and Julie by Sandra. Okay, so they pushed each other over an icy surface, frictionless ice surface, and as a result they move away from each other. So what's the David's speed? So here also we use the conservation of momentum. Momentum before pushing is equal to momentum after pushing. So here the system is Sandra and David. So momentum of Sandra plus momentum of David, and momentum of Sandra plus momentum of David. Here we are talking about initial, so SI, DI, I, and the formula for momentum is mass times velocity. So here mass times velocity, mass times velocity, mass times velocity, mass times velocity. But now we need to differentiate which one is which one. So here we are talking about Sandra, S, mass of Sandra, and then velocity of Sandra, initial, mass of David, velocity of David, initial, mass of Sandra. Mass doesn't change, so we don't need to write I or F for mass. Velocity of Sandra. So this one should be final. Sorry, it might take it. I need to correct that. This is after pushing, so after is final. So that's final. Mass of David, velocity of David, and it's final. Okay. Now you need to plug in the numbers. So here we want to get velocity of David, final. That's what we want. So initially they are both at rest. So their velocity, this one is 0, this one is 0. So 0 on left side. Mass of Sandra, 45 kilogram. And velocity after pushing is 2.2. And this is positive because it's moving to the right. Okay. Plus mass of David is 80 kilogram, and velocity is unknown. So do the math and then you'll get velocity. So okay, I will let you guys do that. Okay, so I want you to figure out what this is and give me a number. Do you have a negative sign or is it positive?
Wait. Oh no.
Sign is very important in this case because sign tells us which way he is moving.
It'd be negative, wouldn't it?
Yes, so you'll have negative sign. So what's the number? (45 times 2.2 over 80). 1.24. Okay, meters per second. So this negative sign implies that David moves to the left after pushing each other. Okay, now let's look at this two-dimensional problem. So far we saw the motion in one dimension or conservation of momentum in one dimension. But now let's see how we solve the problem when it involves more than one dimension. So number 4. So we have two objects sliding over a frictionless horizontal surface. You have some kind of surface, and you have this object, and this object. The first object with mass m1 is propelled with speed of v1I. Okay, that's the speed of the first one, or velocity. It moves towards the second object that has the mass of m2, which is initially at rest. So initially this is v2I is 0. After the collision, both objects have velocities which are directed 30 degrees on either side of the original line of motion. So original line of motion is this one. Okay. So one object moves this way at 30 degrees to that line, and the other object moves also at 30 degrees but below that line. Okay. So let's say m2 moves along this line and m1 moves along this direction. So that means the velocity of this one would be velocity of the second mass and its final. Okay, after collision means final. So this one is velocity of the first one and it's after collision. Okay, so that's the scenario here. Now, when we have two dimension like this, when it's not along a single line, we need to deal with x-axis and y-axis separately. Okay, so you need to use conservation of momentum separately along x and y direction. So for that, let's define the coordinates. So this is y-axis. Choose the object that is at rest as an origin. Okay, so this is origin. So this is our x-axis, and that's our y-axis. So let's use conservation of momentum along x-axis. So along x direction, conservation of momentum before collision is equal to total momentum after collision. Okay. So momentum of 1 plus momentum of 2, okay, is equal to momentum of 1 plus momentum of 2, and this is before collision, after collision, after collision. So what's the mass, what's the momentum? It's mass times velocity, mass times velocity, mass times velocity, mass times velocity. Mass is mass of 1, mass of 2, mass of 1, mass of 2. Here velocity is the velocity of 1 initial, velocity of 2 initial, velocity of 1 final, velocity of 2 final. Okay. Now here we are only looking at the motion along x direction. Okay, don't look at up or down, just look at this direction. So before collision, m1 is moving along x direction, so all this is along x direction. m2 is at rest, okay, before collision, so this is 0. Okay. So that's 0. m1. Now for x direction, what is the velocity of v1 final? v1 final is moving this way, but we only care about the x direction. That means what's the x component of this one? This is given. So what's the x component of this one? We want to write the x component. Yes. So v1 final cosine 30 degrees. Okay. plus m2. Likewise, what's the x component of this one? v2 final cosine 30 degrees. And again, this is because we are focusing only along x direction. So that's for the x direction. Now let's do the same thing for y direction. Which one is negative? All are moving in the same direction. They are all moving along the positive x direction.
I didn't know if the cosine would be negative.
You mean this should be negative?
Well, since it's in the fourth quadrant.
Yeah, you are right. It would be negative for y-axis, but not for y. So here is your vector. Its x component is this one, right? That's vx, and y component is this one. So this component would be negative because it's down, but this component is still towards the positive x, right? So this is positive, but that's a good point. So we'll see that along the y direction. So in y direction, so this one doesn't have any y component. It's all along x direction. So that means 0 for the y component of the momentum is 0 for this one. How about this one? Is there any y component for this one? Is it moving up or down? No, right, before collision. Just like this one, it's not moving up or down. That's why it doesn't have any momentum along y direction. So this one also is at rest, so no momentum along y direction. Now, after collision, this one has a part along y direction, and that's what we are looking for, which is v2f. What is the y component of that one? v2f sine 30 degrees. Likewise, this one has part along x and part along y, and we are looking for the y part. Okay, y part is, like you said, so that would be negative because it's pointing down. v1f sine 30 degrees. Okay. So we got this equation, call that 1, and that equation, call that 2. Now often you guys get confused once you have this kind of equation, so what to do with that? Okay, you have like this long equation. So then next step would be think about what you want to find. Let's see, someone has a question. Do we not need mass for y direction? Yes, that's right. Okay, thanks for reminding that. I forgot to add the mass because we are dealing with the momentum here. So this is m2, m1. Okay, I forgot the mass. Okay, so again, think about what you want to find. Okay, that's the thing you need to think about. So read the question and see what it's asking. Find the final speed of the two objects. So we want to find v1 final and v2 final. That's what we want. So to find that, so both these equations have v1 final and v2 final. That means we need to somehow eliminate either v1f or v2f from the equations. That's the way to solve the problem, right? So it's like you have a plus b is equal to 2 and a minus b is equal to 3. And then how do you solve these two equations? You eliminate either a or b and then find the variable, right? Like eliminate b, and then you get 2a is 5, and then you solve that. The same kind of thing here, okay? So how do you eliminate v1 or v2f on this equation? So you can simplify this. Let's simplify this and see what you get. So to simplify this, take this term to the right. So you get m1 v1f sine 30 degrees is equal to m2 v2f sine 30 degrees. Okay. Taking to the right means you can also add this term on both sides. You get the same thing. Okay. It's just different way to do the same thing. So I'm just transporting this whole thing to the left. And then sine theta and sine theta are common on both terms, so I can cancel that. So I want to eliminate either V1 or V2, so I will write this equation in terms of V1F. So M2, M1, V2F. Okay? And then I can use this in this equation. And that's how I can eliminate V1F from this equation. And then everything here would be known except V2F, which we can find. Okay? So let's do that. So let's call this equation 3. So replace or just substitute V1F from 3 into 1. So M1 V1I, okay, M1. So I'm replacing this V1F by that. So M2 over M1 V2F. The reason for doing that is again just to get the equation in terms of one unknown instead of two unknowns. That's cosine 30 degrees plus everything else is same. Okay. So now in this equation we know everything except this quantity. So this is what we want to find. Masses are given, initial velocity is given, cosine 30 degrees is known. Okay. So you want to somehow write this equation in terms of VF, V2F. So I have M1 V1I. So we have V2F and V2F common on both the terms. Can you simplify this? What can you do with this? Yeah, cancel M1 and M1. So then M2 cosine 30 degrees. So this we can take outside the parentheses because they are common, plus M2. I mean, actually they are both same, so I think you can just add them. You don't even need to take outside the parentheses. Okay, so let me just add. Let me rewrite that, and then you'll see they are same. Okay, M2 V2F cosine 30 degrees plus M2 V2F cosine 30 degrees. Okay, it's same thing. So when you have two same thing, what you can do is you can add them. Okay, so this is 2 times same thing. M2 V2F cosine 30 degrees. So now you express this in terms of V2F. Okay, how you do that? You want to get this, so you divide both sides by the things you don't want on the right side. So 2M2 cosine 30 degrees, 2M2 cosine 30 degrees. Cancel 2 cosine cosine, M2 M2. So then you have V2F, M1 V1I, 2M2 cosine 30 degrees. So plug in the numbers now. Everything is known. Mass 1 mass 1 is mass 1 is what? 5 kilogram, yes. So 5 kilogram, 2 times mass 2 is 2.5 kilogram, and then cosine 30 degrees, and then initial velocity of 1 is given, 4.5 meters per second. Okay, so that will give you, okay, so that and that, so 4.5 over cosine 30 degrees. Can you check that, what you get? Is that 5 point something? 5.2, okay, 5.2 meters per second. Yeah, okay, good. And then once you have that, now you can use either one to find V1F. Okay, so you have, go back to the equation. So use the one that is the simplest one. So let's use equation 3. Okay, so here this one. So we want to find V1F. M2 is 5. Sorry, M2 is 2.5.
So we're trying to find V1F.
Yes, 2.5. We already found V2F. Now we want to find V1F. So that's 5 kilogram. That times V2F is, got 5.2. So that will give us 2.6 meters per second. Okay, that's that. Now we want to figure out whether or not it's elastic collision. Okay, so find the total kinetic energy before collision. So for energy, energy is a scalar quantity, so you don't need to worry about vectors. So energy is a scalar, so no need to worry about direction. It doesn't have direction. So energy before collision is energy of the first mass, second mass is at rest. So 1/2 mv initial squared, or you can also say, let's say, mv2 initial squared, but this is 0 because it's at rest. So 1/2 initial speed and mass of the first one is 5 kilogram. Its initial speed, we found that. No, it's given 4.5. So that gives us 50.6 joules. Okay. Now kinetic energy final or after collision, 1/2 mass 1 velocity 1 final squared plus 1/2 mv2 final squared. Okay. No need to worry about the duration. Just use this velocities. So 1/2 mass 1 is 5. Final mass, final velocity of 1, 2.6, 1/2 mass 2 is mass, wait, did I use the correct mass? Yeah, mass 2 is 2.5, that's right, okay, 2.5, and then velocity 2 final is 5.2 squared. So if you do the calculation, you get 50.6 joules. And what you see here is initial kinetic energy is equal to final kinetic energy. Now you can decide whether it's elastic or inelastic. If it is elastic, then there's no loss of energy. So since no loss of kinetic energy, so it's elastic collision. Okay. So we have one more left. We'll continue this in the next class. There is a quiz due today, so please complete the quiz by the end of the day. And new homework will be available sometime this afternoon or over the weekend, which would be due next week.